This video deals with rotational kinetic energy and angular momentum. Now, before we get to kinetic energy, we're going to talk a little bit about work in rotational systems. And work is equal to the net torque on an object times theta, the angular displacement through which the torque acts. So you can see on this diagram here, this is a disk. We've got a force here, a net force that's acting perpendicular to the radius, and this force exerts a torque because it's a distance here from the center, and it exerts it over, causing the disk to rotate through this angle theta. So the work that would be computed would be the magnitude of the torque times whatever this angle was. And notice also that the units for work in rotational systems are joules, just like they are in linear systems. And of course, if you multiply the units of torque, which is Newton times meters times the radian really doesn't have any units, so you just get back Newton times meters, and in that case, it's equal to a joule. Rotational kinetic energy is defined by this equation, 1/2 IW squared. Notice the similarity between that equation and the one for linear kinetic energy, which was 1/2 mv squared. The units are joules. Okay, so the work energy theorem says that the work done is going to be equal to the change in the rotational kinetic energy of the disk. So this would be the final rotational kinetic energy. This would be the initial. So let's try a problem. We've got a person who spins a grindstone by applying a 200 Newton force through a displacement of 1 radian. The force is perpendicular to the grindstone's 0.320 meter radius. We want to compute the work done and the grindstone's final angular velocity and the final kinetic energy of the grindstone. The mass is 85 kilograms. Okay, so the first part is pretty easy. We compute the work done. The work done is going to be the torque times the angular displacement. The torque is going to be the 200 newtons times the 0.32 meter radius, and the angular displacement is just 1 radian, so that's 64 joules. Okay, now to find the grindstone's final angular velocity, we first must compute the angular acceleration. So we're going to go to the rotational equivalent of Newton's second law, which says that the angular acceleration is equal to the torque divided by the moment of inertia. Okay, so that means we've got to compute the moment of inertia. Now the grindstone is a disk, so we're going to be using 1/2 mr squared. So we have 1/2, 85 kilograms, the mass of the grindstone. This is the radius of the grindstone, so that comes out to be 4.35 kilograms square meters. So now the angular acceleration is the torque, and we get that from the 200 newtons force and the 0.32 meter radius, so that gives us that torque. And of course, I, we just computed over here, was 4.35 kilograms square meters. So that gives us 14.7 radians per second squared. That's the angular acceleration. So now we go back to our kinematics formulas. We can use this one to find the final angular velocity. The grindstone is starting from rest, so that's 0. So that's going to be 2 times the angular acceleration, which we computed here, and the angular displacement, which was 1 radian. So we multiply that out, take the square root, we come out with 5.42 radians per second as the final angular velocity of the grindstone. Now, we want to find out the rotational kinetic energy. So that's 1/2 IW squared. 1/2 I we computed up here. W, the final angular velocity, we computed here. Square it. That comes out to be 63.9 joules. Okay, so notice that the work done here, which was 64 joules, is equal to the change in rotational kinetic energy. This came out to be 63.9 just due to rounding errors as we went through all the computations. But this number and this number are the same. Objects rolling down inclines. Okay, so as an object rolls down an incline, it's going to lose potential energy, but that potential energy is going to turn into both rotational and linear kinetic energy. So let's use a uniform disk or a cylinder as an example and get an expression for what the velocity would be at the bottom of the incline. So we start off by setting mgh, the potential energy, equal to the kinetic energy, 1/2 mv squared, and the rotational kinetic energy, 1/2 IW squared. Now, since we are using a uniform disk, for I, we're going to substitute the 1/2 mr squared, and for the W, we're going to use the equation V over R, which we've seen before. And so if we substitute in here and in here, notice that the masses will all cancel, and also notice that the radius squareds will cancel. So after you do the cancellation and you solve for V, you end up with V is equal to the square root of 4gh, which would be the velocity at the bottom of the incline. Now this is very interesting because the velocity depends only upon the shape of the object, not its radius or its mass. So this equation would be true for a cylinder, any cylinder. Doesn't matter what its size, what its mass. This equation would hold true. Now in my face-to-face class, we usually have a race between a cylinder and a sphere and a hoop, and you can do this same kind of analysis for those two objects and predict what their velocity would be at the bottom of the incline and to see who would win the race. So I encourage you to try that. It's not hard. You're just substituting in the different equations for I, depending upon the shape of the object, and you'll come out with two different expressions for V, and the one with the biggest value here, of course, would be the winner of the race. The last topic is angular momentum. Now, angular momentum is defined as the product of moment of inertia times angular velocity. Usually the symbol is L, and again, notice the similarity between this equation and linear momentum, which was mass times velocity, mv. The units are kilogram meters squared per second. Now, just like Newton's second law, we can define torque as the rate of change of angular momentum, delta L over delta T, and there's a couple of problems in your book that deal with this. Now, a very important point is, just like linear momentum, angular momentum is a conserved quantity. So we can say that the product of the initial IW is equal to the product of the final IW. So a good example of this is in ice skating, figure skating. When they extend their arms, they tend to rotate or spin slower. When they pull their arms in, they spin faster. So here's an example. We've got an ice skater spinning at 0.800 revolutions per second, and she's got a moment of inertia of 2.34 kilograms square meters with her arms extended. She pulls her arms in, her moment of inertia changes to 0.363 kilograms square meters. We want to find out her new angular velocity in revolutions per second, and we want to compute her rotational kinetic energy before and after she pulls in her arms. Okay, so to find out her final angular velocity, we can use this conservation of angular momentum, and notice that we're solving for the final angular velocity. And here is her initial moment of inertia, her initial angular velocity, and her final moment of inertia. Notice those units here are going to cancel, and so our final angular velocity will be in revolutions per second, and it is 5.16 revolutions per second. So notice that her angular velocity has increased quite a bit when she pulls in her arms. The last part of the problem was to compute her kinetic energy before she pulled her arms in and after she pulled her arms in. Okay, so the first thing we have to do is to compute the angular velocity in radians per second, because the problem gave it to us in revolutions per second. So you might recall that to convert from revolutions per second to radians per second, we simply multiply by 2 pi, because there's 2 pi radians per revolution. So 2 pi is approximately 6.28 times 0.8, so her initial angular velocity is 5.03 radians per second. We do a similar thing for her final angular velocity, and that comes out to be 32.4 radians per second. Okay, now we can compute her kinetic energy before she pulls her arms in, 1/2 IW squared. There's the moment of inertia. There is her angular velocity, and that comes out to be 29.6 joules. After she pulls her arms in, then her moment of inertia is reduced to 0.363 kilograms square meters, and her angular velocity was 32.4 radians per second, which we square, and this is 191 joules. Notice a much bigger number here than before. And so the increase in kinetic energy comes from the work that she does in pulling her arms in.